everyone. I am Yinyin, currently pursuing the master degree in automation and electronics, Xiangtan University, China. In this paper, we proposed a multi-view three-dimensional reconstruction based on a two-stage multi-level depth network for agriculture applications. Multi-view stereo vision 3D reconstruction is widely applied in many fields, such as unmanned driving, virtual reality, and intelligent robotics. In agriculture applications, the group images need reconstructed in 3D version and have high accuracy or other properties for precision operation. Traditional MVS methods are generally classified into 4 categories, including voxel-based, point cloud-based, grid-based, and depth map-based. May obtain a basic effect and could achieve the good results in aspect of accuracy. However, there are still some problems when facing special conditions and in special region of image, such as shattering, lighting very weak texture region, and non-lam surface. These problems mainly include lack of robustness, low completeness, poor visual perception of human body, etc. In recent years, the methods based on deep learning have been widely researched, which is mainly aimed at improving the reconstruction accuracy of MVS 3D reconstruction. However, these are still worthy of further improvement in terms of storage consumption, computing time, reconstruction completeness, and reconstruction efficiency. Multi-view three-dimensional reconstruction methods based on deep learning can be generally divided into unsupervised learning and supervised learning. These methods are firstly to extract the feature information of the image and then to calculate the depth map and conduct the depth map fusion so as to reconstruct the 3D point cloud. To address the dependence of deep learning 3D reconstruction networks on ground truth, Yang Jiayu proposed a self-supervised deep learning network, self-supervised CBAMs, which first learns depth maps estimated in an unsupervised learning framework as potential pseudo-labels, relying on image reconstruction loss as truth values. The method then uses these pseudo-labels as supervised signals to train the network and iteratively improves the network performance by self-training. Then, M3 VSNet proposed a novel multi-metric loss function that combines pixel-wise and feature-wise loss function to learn the inherent constraints from different perspectives of matching correspondences. In addition, normal depth consistency is added to the 3D point cloud format to improve the accuracy and continuity of the estimated depth map. RCMVSNet contains the geometric features to be close to the object surface by imposing a depth rendering consistency loss to mitigate the occlusion problem of object in real sense. In the same way as unsupervised methods, various supervised methods have been proposed to improve the quality of 3D reconstruction. Yao et al. Propose an end-to-end MVS architecture MVSNet that builds a cost volume upon CNN features and learns the cost volume recognition also with CNS. However, the memory consumption for 3D cost volume grows quickly. Therefore, RMVSNet proposes using convolutional GRU for cost volume recognition and thus avoid using memory intensive 3D CNS. By contrast, pointer MVSNet uses a cross-to-find strategy that first predicts a low resolution depth map and iteratively unsimpled and refines the depth map. Faster MVSNet first construct a sparse cost volume for learning a sparse and high resolution depth map, then leverage a small scale convolutional network to encode the depth dependencies for pictures within a local region to decipher the sparse high resolution depth map. At last, a simple but efficient Gauss-Newton layer is proposed to further optimize the depth map. Where these methods have shown impressive results, their efficiency is still far from satisfactory. In this paper, we propose a two-stage multi-level depth learning network to predict depth maps in a cross-to-find evolutionary manner. Its whole network structure is shown in Figure 1. In the stage 1, it mainly focuses on generating different hierarchical feature maps using the attention-enabled feature pyramid network. In the stage 2, it mainly focuses on depth map prediction by multi-level processing. In each level, the outputted depth map is obtained through 5 critical steps. That is, feature extraction, cost volume construction, matching cost computation, cost aggregation, and depth map regression. In the stage 1, the inputs are n images which contain 1 reference image and n-1 source images. By embedding convolutional attention models in the different hierarchical lateral connections of the FPN, a feature maps containing the shown and deep semantic information can be generated. A fusion of different hierarchical feature maps obtained from the top to down pathway or upsampling processing of the FPN and the same hierarchical convolutional attention model is carried out. As a result, there are different resolution feature maps are constructed. They are correspond to 1/2, 1/4, and 1/8 of the input image size, respectively. In the stage 2, the different hierarchical feature maps obtained in the stage 1 are processed through a series of processing to predict the different level depth map. In the output part of stage 2, the depth map generated in the level 1 is upsampled. Then fusing the refined reference image through the depth region network, the final depth map is obtained. We introduced a convolutional block attention model whose structure is illustrated in Fig 2. Assuming the figure map F as its input, the convolutional block attention model sequentially inflates the one-dimensional channel attention feature map FC, as well as the two-dimensional spatial attention features maps FS. The reason for embedding convolutional block attention model in lateral connectively of appearing as is mainly because that the difficulty of distinguishing foreground and background in different region feature maps in appearing as. The final features could be obtained by enhancing the correlation of channel and spatial information of feature maps in the appearing networks, and mainly the mutual interdependencies of different features at different scales. The proposed method was evaluated in terms of three assessment metrics, namely accuracy, completeness, and overall. The quantitative parameters of 15 methods of multi-view stereo vision 3D reconstruction were calculated and constructed. The results are listed and constructed in Table 1. The broad indicates the best value. It can be seen that the method GPUMA performs the best performance in accuracy. Trans-MVSNet performs the best value in overall. Our method significantly outperforms other methods in completeness. The subjective evaluating results are depicted in Fig 3. As shown in the figure, the depth maps and the point cloud maps for a typical patchMatchNet network and our proposed network. The ground truth depth map and the input image are provided. It can be seen that the depth map obtained by our method has less noise and looks smoother. This is primarily due to the introduction of the attention mechanism. In Fig 4, the images processed by our network, RMVSNet and patchMatchNet, are provided and contrasted. Meanwhile, the standard GT is given. For the first row of images, scan 9, it can be seen that our proposed method performs better human visual perception and obvious features in the region framed by the red line. For the second row of images, scan 11, the dashboard scale is clear for our method, as seen from amplifying region. For the third row of image, scan 33, both the toggle airball profile and the data features in the middle region are more abundant for our method. To investigate the computational complexity and the memory consumption for the proposed method, The experiments were carried out on detailed evaluation set. The resolution of the input images is set to 164 multiplied by 1152. Considering the memory limitation, the results are listed in Table 2. It can be seen that the testing time for our method can be reduced by 74%, 64%, and 51% compared to the methods of trans-MVSNet, CAS-MVSNet, and MVSNet, respectively. In comparison to PatchMatNet, the memory consumption of our method is almost equal, and there is a single reduction in testing time. To investigate the proposed network applied in agriculture, the network model was trained on the detailed dataset without any fine-tuning, and then it was tested on a self-collected agricultural group images. The images of 3 types agricultural crops are collected, which are of textually Gallic and Roman lettuce plants, respectively. They were obtained in the laboratory with 49 views for each group under the same lighting conditions and different perspectives. The obtained original images are shown in the left column of Fig 5. The device used for taking photographs for these groups is Canon EOS 80D. To obtain the camera parameters, the method of CoMap was applied for the spatial reconstruction of the group images, which would calculate the intrinsic matrix and the extrinsic matrix of the camera and the spatial point cloud information. The original images and the output information from the CoMap are imported into the proposed network to reconstruction the dense point cloud. The experimental results are illustrated in Fig 5. It can be seen that the point clouds reconstructed by the proposed network has fewer false matrices in comparison to PatchMatNet, and the reconstruction point clouds are more complete and perform better human visual perception. In this paper, a 2-stage multi-level 3D reconstruction depth network using an attention mechanism is presented. Through the employment of the CBAMs in the stage 1, the spatial and causal correlation in different hierarchical feature maps in the APN could be enhanced, and more abundant actual texture information could be generated by the foreign multi-level processing in the stage 2. The objective experiments show that our method performs better 3D reconstruction effect in completeness and lower computational complexity. The subjective experiments show that our method performs good human visual perception. Moreover, the proposed network could be a candidate for agricultural crop image processing. Thank you for your watching.